Today we'll be talking about the cardiac cycle. This image can be very overwhelming at first, but we're going to break it down into simple parts to better understand it as a whole. The cardiac cycle is as it sounds. It is a graph that describes what the heart will do in one cycle or one heartbeat. Remember that in a normal healthy individual, a normal heart rate is about 60 to 100 beats per minute, meaning that we can go through this graph, or your heart can, about 60 to 100 times in 1 minute. First, we need to know that this graph is only representing the left side of the heart. The right side is just as important, but the left side gives us a better representation of the cardiac cycle. Notice that the cardiac cycle is described by a couple of actions of the heart. Heart sounds, which are the sounds you often hear as lub-dub, EKGs or electrocardiograms, which show the electrical current of the heart, ventricular volume or blood volume of the left ventricle. This is how much blood is actually in the left ventricle. Ventricular pressure, atrial pressure, and aortic pressure. We will go into more detail about each of these later on throughout the video. These actions, though, are further broken up into segments on the cardiac cycle. These segments have specific meanings and timing of the heart's actions, but once again, we're going to go into more detail about this later. First, let's go over how the blood flows normally through a healthy individual.
The heart is made out of muscle that contracts and relaxes like a pump, generating pressure pushing blood throughout the body and to the lungs. Blood circulation to the body is known as systemic circulation, and blood circulation to the lungs is known as pulmonary circulation. The heart is composed of two pumps, though. The right side receives blood from all the veins in the body, or systemic circulation, to pump to the lungs. This blood coming back to the right side of the heart lacks oxygen or is deoxygenated. This blood is then pumped from the right side of the heart to the lungs to get reoxygenated in exchange for CO2. Then this blood returns from the lungs, being rich in oxygen, is received by the left side of the heart. The left side of the heart pumps this blood throughout the body. The left side of the heart is responsible for pumping this blood systemically to keep vital organs and tissues alive with rich oxygenated blood.
Now that we know how blood moves through the body, let's understand it more specifically in the heart. This is important to understanding the cardiac cycle. The heart is divided into 4 chambers. There are the right and left atriums and the right and left ventricles. Remember, the right side of the heart is responsible for pumping deoxygenated blood to the lungs. Blood is constantly flowing into the right atrium from systemic circulation and will open up a one-way valve or door to flow into the right ventricle. It is important to note that all valves open and close because of pressure that is generated by the heart contracting and relaxing. This is related to Boyle's law that states there is an inverse relationship between volume and pressure. When we increase volume, we decrease pressure, and when we decrease volume, we increase pressure.
Applying Boyle's law to the heart, as the atriums both contract at the same time, the space in the atriums decrease, or the volume decreases, which increases pressure, forcing the blood in the atriums to open the tricuspid and bicuspid valves and fill the ventricles. Now that blood has filled the ventricles, the muscles surrounding the ventricles will begin to contract, decreasing the space or volume inside the ventricles, which will increase the pressure. It is important to note that the tricuspid and bicuspid valves are one-way valves. They cannot open to allow blood to flow from the ventricles back into the atriums. When ventricular pressure is greater than the atrial pressure, these valves will close. Remember, pressure opens and closes valves. Papillary muscles prevent these two valves from opening backwards, preventing the blood from flowing from the ventricles back into the atriums. These muscles are pulling the valve shut as blood from the ventricle is trying to push it open the other way because of the rise in pressure. Imagine trying to push the door open while someone else is pulling it closed, preventing you from opening the door. These papillary muscles prevent blood from regurgitating back into the atriums by preventing the valve from prolapsing or flopping back into the atriums. This design of the heart then forces the blood through the pulmonary semilunar valve and aortic semilunar valve. Remember, pressure opens and closes valves. So in order to open these valves, the pressure in the ventricles has to be greater than the pressure in the pulmonary artery and aorta. The left semilunar valve, also known as a pulmonary valve, feeds blood from the right side of the heart to the lungs, and the aortic semilunar valve feeds blood from the left side of the heart to the body. Now, you may be wondering, how does the heart know when to exactly contract and relax to push blood around the body? This is accomplished and controlled by the electrical conduction system of the heart. This electrical system is like electrical wiring to a house, except this is going to be the electrical wiring of the heart. The heart muscle does not contract or relax unless told to do so by an electrical impulse. The electrical impulses begin at the sinoatrial node, or SA node. The SA node dictates the pace of the heart and is usually sending electrical impulses anywhere between 60 to 80 times per minute. The electrical signal is then sent through the wiring of the electrical system to the rest of the heart. It will travel across Bachmann's bundle to the left atrium and down towards the atrioventricular node, or AV node. This signal can be measured using an electrocardiogram, or ECG. Sometimes it's referred to as an EKG. You may have seen this machine before, but it only measures the electrical activity of the heart, and not the actual heart muscle itself, or the contractions of the heart. How it does this is by strategically placing electrodes on specific areas of the body. When there are no electrical impulses, the machine will display a flat line called isoelectric. When we do have electrical impulses traveling in the heart, it will cause a deflection to occur. A deflection is a deviation from isoelectric, and it can either be a negative deflection, going below isoelectric, or a positive deflection, going above isoelectric. What dictates a positive or negative deflection depends on which way the signal is traveling and towards what ECG electrode. These electrodes are either positive or negative. In this image here, we can see that if the electrical signal is traveling towards a positive electrode or lead, we will have a positive deflection. If the electrical signal is traveling towards a negative electrode or a negative lead, then we will have a negative deflection. We can also see that if the signal doesn't exactly travel towards an electrode or lead, but it's traveling in that general direction, then it will still elicit a negative or positive deflection, but it just won't be as strong. If the signal is traveling in neither direction, then the signal goes both ways. Now, returning back to the heart, if we were to place a negative electrode here and a positive electrode here, we will be able to map out the electrical impulses with an EKG. A normal heart EKG looks like this. Remember, the SA node sets the pace of the heart and controls the rate at which the heart beats, and the heart doesn't contract without these impulses to push blood around. Now, the signal that was sent from the SA node traveling towards Bachmann's bundle and down towards the AV node is not a direct electrical impulse to that positive lead. Now, if the electrical signal is not heading directly towards a positive lead, but is going that general direction, what type of deflection would you expect? A positive deflection, because we're traveling in the general direction towards that positive lead, which is going to elicit a small positive deflection. We call this deflection the P wave, which means atrial depolarization. Depolarization does not mean contraction of the heart. Depolarization is just the signal being sent to tell the heart to contract. During the PR segment on the EKG is when the actual contraction of the atriums is occurring. Now, during the PR segment, when the atriums are contracting, notice how there are no electrical impulses being sent, hence the isoelectric wave that we see. This is because of something called the AV node delay. The AV node will actually delay the signal that was sent from the SA node. This is a good thing. This allows the atriums to fill the ventricles with as much blood as possible before they begin to contract. After the delay, the signal is then sent and continues through the bundle of His. Notice how the signal is heading in a direction between the positive and negative lead. If the signal is going neither towards the positive lead or the negative lead, what type of deflection will occur? An upward or downward slight deflection. In this case, the heart will elicit a slight downward deflection toward Q. As the signal travels down the bundle branches, it is heading directly towards a positive lead. If we are heading directly towards a positive lead, what type of deflection will we see? A positive deflection. And we see this on the EKG from Q to R. Now once the signal hits the apex of the heart, it will travel up the walls of the ventricles through Purkinje fibers, definitely one of my favorite words, heading directly back towards a negative lead. What type of deflection will we see if it's heading back towards a negative lead? A negative deflection that we can see here on the EKG from R to S. We call this QRS wave the QRS complex, which means ventricular depolarization. Remember, depolarization is the electrical impulse being sent. It is not the actual contracting of heart muscle. That occurs during the ST segment on the EKG. The last wave to occur is the T wave. The T wave represents ventricular repolarization. Ventricular repolarization will lead to the relaxing of the ventricles so they can fill back up again with blood. This repolarization will elicit a positive deflection as seen here on the EKG, which means we are heading back towards that positive lead. Now we are ready to put this all together on the cardiac cycle in another video. Thank you so much for watching this tutoring video on the cardiac cycle.